Okay, so welcome back, everyone. Our last speaker this morning is Jérémie Szeftel from Paris, and it's a very great pleasure. We look forward to your talk on the nonlinear stability of Kerr for small angular momentum.
Thank you very much. Well, thanks a lot to the organizers for inviting me. It's always a great pleasure to be in Vienna, and it's particularly a pleasure this time to be there for the 100th celebration of the 100th year of Yvonne. Okay, so Sergio gave a fast introduction, but I think I will still spend a little bit of time on history because that will allow me to introduce some of the notations that you did not have the time to introduce. So let me quickly remind you the conjecture. So you are in the setting of asymptotically flat solutions to the Einstein vacuum equations. And the stability is in fact not the stability of the entire maximal development, at least maximal solution, but in fact the stability of the exterior region, the black hole. And to the Kerr black hole, and the conjecture is that small perturbations of given initial conditions for an exterior Kerr in the sub-external range. So I'm going to present the Kerr solution in the next slide, but it's a two-parameter family of solution, and you look at the sub-external range, in other words, absolute value of angular momentum is strictly less than n, then the solution should be global and converges asymptotically back to the Kerr family, except that in generically it converges to a different member. So part of the problem is particular to track the final parameters of the solution, which is the final mass, the final angular momentum, and as we'll see later, in fact, a big part of the problem is to track the final diffeomorphism in which you see your Kerr solution. Okay, but this will be for later. So what I want to do, I want to quickly review the history of the problem and introduce some notations, and then I'll state, well, I'll restate the result that Sergio already stated on the resolution of this conjecture for small angular momentum. And finally, at the end, I want to focus on one particular aspect of the proof, which hopefully is maybe more interesting to this audience, where there are lots of geometers, where I will construct specific foliations by spheres. So maybe I can that can be related to some of the interest of the audience. Okay, so let me quickly review the Kerr metric. Actually, I'm not sure that it has been explicitly written in this conference. And given the formula, you can understand why. So the Kerr metric, first of all, it's not one metric, it's a two-parameter family of metrics, which are which depend on two parameters, which is the mass m and the angular momentum of the Kerr black hole. And you can see that this formula is explicit here. I am giving you the formula in one particular coordinate system, which is called Boyer-Lindquist, so TR theta phi. And you can see in particular that so first of all, I claim that this is an explicit solution to the Einstein vacuum equations. That was the finding of the seminal paper by Roy Kerr. So nowadays, you know, you can check it with Mathematica. It's not so easy to do. But here, none of the metric coefficients depend neither on the time coordinates nor on the phi coordinates, which means that you have a stationary metric and it is also axis symmetric. Okay, and in particular, the main feature, in fact, which I did not explicitly write here, but I mean, I just saw it contains a black hole. So the main feature of this solution is that it contains a black hole region, which is located at the largest root of this second order polynomial here. Okay, and finally, let me mention a last property, which will play actually an important role. It's the fact that the Kerr solution possesses a distinguished pair of null vectors. Okay, so here in the talk, I will without choke. So sorry, yeah. Okay, so in the talk, I will always consider null pairs. So E3, E4 will be two null vectors. And when I say null pair, that means that for me, I normalize them. G, E3, E4 is equal to -2. So maybe let me recall, of course, the usual null pair of Minkowski. I mean, I guess the one you have in mind, which is E4 is dt plus dr, and E3 is dt minus dr. So that would be my null pair in Minkowski, by ferring that pair, let's say, in radial, expressed in radial coordinates. Okay, and we can immediately show that it satisfies these things in Minkowski. And then I'm simply saying here that the analog of this null pair is the one which is explicitly written here in thank you, in Breuer-Lindquist coordinates. And so here you could say, in what sense is it I mean, what is special about this null pair? So we'll see maybe in the next slide or maybe a bit later. What is special about this null pair is that it diagonalizes the curvature tensor in Kerr in some sense that I'm going to show. In other words, it achieves the maximal number of zeros of the curvature component. Okay, and here let me do just one last remark. I will not really have the time to talk about it today, but when the angular momentum is non-zero, this term here is responsible for the fact that this null pair is non-integrable in the sense of Frobenius. In other words, if I look at the orthogonal space E3 and E4, then it generates a two-dimensional space, which is not the tangent space of any manifold. So this non-integrability is in fact part of the difficulty when you go to Kerr where you have a Kerr with non-zero angular momentum. But I mean, I'll talk a little bit about it today, but unfortunately not much. And in particular, this is not the case, of course, in Minkowski nor in Schwarzschild, in which case this pair is integrable. And in fact, let me end this slide by mentioning that if you restrict to the partial case of angular momentum zero, you get back the Schwarzschild matrix. Okay, so here are the basic quantities. So you have a null frame. So here, so far, I only talked about the null pair. To get a null frame, you take your null pair, and then you add two vector fields to complete the frame. So these two vector fields span is a orthonormal basis. E1, E2 is an orthonormal basis of the orthogonal space to E4. Okay, so for instance, maybe again I can draw a picture in Minkowski, which again is different from Kerr because it's the integral case. So in Minkowski, if I look at, for instance, an outgoing null cone, then E4 would be the generator of outgoing null cones. E3 would be the generator of ingoing null cones. And E1, E2 would span the tangent space of the round spheres of intersection between outgoing and ingoing null cones. And here, let me just say that in Kerr, the only difference is that if the angular momentum is not zero, now you're non-integrable. So again, let me recall that if you look at the orthogonal space, you can still define E1, E2 as spanning the orthogonal space of E3 and E4. So this would be spanned by E1, E2, at least locally, in other words. But now these are not this is not tangent to any sphere, any close to surface. Okay, so from now on, so this I will always work with frames. So this is the, if you forget about the issue of non-integrability, this is in fact the framework of the stability of the Minkowski space by Sergio and Demetrios. And then you can, using this null frame, you can start looking in particular at connection coefficients and curvature components. So as usual, you have a bunch of terms here. So in the framework of Demetrius and Sergio, this is a bunch of Greek letters. And let me just mention two of, well, okay, they have a meaning, right? They all have a joint meaning, but they, if you see it for the first time, it just looks like a long list. But they correspond to, so let me single out only these two ones because these are the ones I'm going to refer to later. So chi and chi bar are in fact the, at least in the integrable case, these are the two null second fundamental forms, respectively, of ingoing and outgoing null cones. Okay, and finally, for the curvature component, again, you have a long list of Greek letters. And here, let me only emphasize the one we'll see in the talk. So the main ones for this talk are alpha and alpha bar, which achieve the maximum number of contractions with either E4 or E3. And finally, beta, which has a different set of combinations, but as it will turn in the last part of the talk, I wanted also to write it explicitly down. And finally, let me come back to this issue that the principal null directions diagonalize the curvature tensor in Kerr. So here, everything I'm writing is in perturbation of Kerr. So I'm thinking of my null frame to be a perturbation of the exact null frame of Kerr that I gave in the previous slide. But at least if you are in the principal null frame of Kerr, then this is at least as far as curvature is concerned, this is the degree of vanishing that you achieve. You achieve that almost all components vanish, except the two middle ones here, rho and rho star, which are two scalar functions. So out of 10 degrees of freedom, that you have, there are only 2 left in Kerr. Okay, so this is why you want really to linearize your objects. You want to think of perturbations of the principal null frame. This is exactly to achieve all these cancellations, which will be very useful when analyzing the system. Okay, so let me now start with something. So we heard already a lot about the linearized system. So when you talk about stability, you want to linearize your equations around the objects for which you study stability. So here I want to derive the so-called linearized gravity system, which are simply the linearized Einstein equations around Kerr. Okay, so for this I have 2 sets of equations. I have the null structure equations, and I have so I have the equations for the gammas for the connection, and I have the equations for the curvature components, which I'll denote by R. And here let me just write these equations very symbolically or schematically if you want. Usually you have a system of 20 equations for both equations. So I don't want to impose on you this very large system. So let me just write symbolically how it looks like. It looks like derivative of the connection plus connection dot connection is equal to curvature, and derivative of curvature plus gamma times curvature is equal to 0. So this is exactly what you would expect, except that of course you have to do it for any possible direction and any possible contraction. So this is why you get it's a 40 by 46. Okay, so here maybe I should have said this is this comes at after projecting the Bianchi identities and using of course the Einstein equations. So in fact the only place where the Einstein equations are actually used on this slide is for these equations. Okay, and then what you do is you want to linearize your system around Kerr. So you're going to write that the gamma are equal to the actual Kerr value plus something which is linear in the perturbation. So I will say O of epsilon for linear in the perturbation. And same for curvature, I want the value in Kerr plus something which is linear in the perturbation. And then I want to plug this decomposition in these equations, again in these symbolic schematic equations. And then schematically, this is what I get when I expand. When I expand, the 0-order terms vanish because Kerr is itself a solution. You're linearizing around the true solution of the equations. And then you get first order terms, first order in the linear perturbation. These are the terms in red here. This is the linearized system. And finally, you get quadratic and higher order terms, which I will simply denote by O of epsilon square. Their structure is very important. I mean, it was mentioned several times in this conference, in particular by Seiju, that they should satisfy the null structure. But when I review the history of the linearized problem, let me first forget about them, even though they're of course crucial, and just focus on the terms in red here. Okay, and here what I would like to mention is that in the case of Kerr, this is you end up with a very large and entangled system. And let me make a remark on what simplifications you can hope if you look at stability of Minkowski. If you look at stability of Minkowski, then now curvature Kerr is now curvature Minkowski, and of course it's flat, so it's 0. And therefore this last term here vanishes. And if this last term vanishes, then suddenly you see that there is a decoupling between the two equations. You had first control the equation for our check, and then plug here and see these equations for the gamma check, so the linearized connection coefficients with the R check as a right-hand side. So in Minkowski, you get this very nice decoupling, which is heavily used in the proof of Demetrius and Sergiu and in later proofs. But here in Kerr, it turns out that the linearized system is very entangled. There is not this disentanglement because precisely the curvature, even if lots of components vanish in Kerr, and not all of them vanish, and therefore this is quite common. So let me quickly review how the physicists approach this problem. So here I said that there is a large literature about this problem in the 60s and 70s, but in fact it started in the 50s and ranged all the way to the 80s. And here I'm mentioning, so there are lots of names. I'm mentioning the names, in fact, that will pop up again later in the talks. So the names of Roger Wheeler, Tucholsky, Chandrasekhar, and Whiteley. Okay, so what do you want to do? So you want to analyze linearized gravity system, and because it's large and entangled, you want to draw an analogy with linear system, which I think we already heard in the talk of Stefan. Of course, when you have a full matrix, the best thing you can hope is to use Gauss method to put it in lower triangular form. Okay, so if you had a usual linear system, not the system here, which is of course a coupled system of hyperbolic PDEs and other type of PDEs, but if you had a usual linear system and if the matrix was full, what you would like to do as a first step is try to put in lower triangular form. Okay, so that was exactly the idea of Tucholsky. And for that, obviously, if you want to prove to put your system in lower triangular form, there has to be at least one component that for which the equation doesn't see any of the other components. Okay, so this is why. Oh, okay, there's one on this side too. So. Okay, so then this is this requires already to first define first component, and of course these are systems of PDEs, so there's no reason that why this should in fact be true. But it turns out that there is an algebraic miracle which allows Tucholsky precisely to find not that there is one such component, and in fact there are two such components, and these are precisely the extreme curvature components alpha and alpha bar I wanted to single out. Okay, and then if you and then what he writes is a system of wave equations at first order, where wave equations on Kerr for tensorial quantities with a first order and zero order term. And in particular, I put the first order in red here, is they are responsible for these equations not deriving from a Lagrangian, which from the point of view of what you want to do, which is proof decay, is a significant difficulty. Okay, but let me forget about this aspect, which we're going to see back in the next slide. And for now, let me just say that from there, the strategy is pretty clear. You want to first derive decay for the Tucholsky scalars, at least if you follow the idea from the physics literature, and then you want to go on to control the rest of the linearized gravity system by exhibiting a triangular structure. Since Tucholsky is central, let me start, in fact, by reviewing very quickly, because you already essentially covered all the references. So let me quickly review what was done for decay for Tucholsky. And as Sergio mentioned, of course, Tucholsky is a tensorial system of wave equations with first order and zero order terms, which does not derive from Lagrangian. So it's a good idea to start with a much simpler problem, which is in fact already significantly, in fact, very difficult, which is just controlling the scalar wave equation on Kerr. And okay, as Sergio mentioned, it took almost 10 years to, in fact, a little bit more than 10 years to completely settle this problem. Here, in fact, there are lots of names one could quote, so I really apologize, but I think we saw already these names in Sergio's talk, so I consider that these are probably the main contributions, at least as far as you want to derive sufficient decay for nonlinear applications. Okay, and so then once you know how to deal with the scalar wave, you want to come back to the Tucholsky equations. And as I said, they do not derive from Lagrangian. It's actually hard to take to control them. And the first result that was obtained was by the seminal work of Whiting, where he could prove that Tucholsky has no exponentially growing modes, which, as Sergio explained, of course, it's very far from being sufficient for nonlinear application. You should see it as the fact that there are no obvious counterexamples to decay, right? If there were exponential growing modes, then there's no hope. But at least if they are not there, there are no obvious counterexamples. Okay, but then you want to really derive quantitative decay, and for this there is this important Chandrasekhar transform that transforms Tucholsky to Regé-Wheeler. But Chandrasekhar, as it's customary in physics literature, was just writing things in mode decomposition. So it was not at all clear that you could really use it for nonlinear applications. You don't really want to decompose in modes. And in fact, it was the main observation of the famous Holzhauer-Rudiansky was to, in fact, realize that this is, in fact, physical space in the particular case of Schwarzschild. And it allowed them in the breakthrough result to, in fact, control Tucholsky in Schwarzschild using this observation, because now Regé-Wheeler, unlike Tucholsky, does derive from a Lagrangian, and then you can apply the methods that were, you can adapt easily the methods that were derived for the scalar wave equation. Okay, and finally, this was extended later independently by Ma and Beffelros, Holzhauer-Rudiansky for the small AK case. And then the larger case, in fact, is a very recent result of Yakov and Rita and of Pascal Mille. Okay, so this is what I wanted to say on Tucholsky. And now let me come back to the linearized gravity system. In other words, the full system, not just the subsystem of Tucholsky. And let me immediately mention that, in fact, in general, you cannot fully solve this problem because there is the presence of a kernel. In other words, so this is, of course, this is something that you expect. This is something very classical, which happens as soon as you look at the stability not of a single solution, but of the smooth multi-parameter family of solutions. So if here, you know that Kerr is a solution which already depends on 2 parameters. And of course, you know also that there is general covariance. In other words, I can pull back by the diffeomorphism and I still have a solution to the Einstein equation. So then this is a smooth multi-parameter family. And now if you take the variation with respect to any of these parameters, automatically the variation will be in the kernel of the linearized Einstein equations, which is the linearized probability system. So if you take the variation, then, well, let me not say with respect to which parameter, but if you take the variation of your multi-parameter family with respect to any of the parameters, then you get a solution of the linearized probability system. So you are in the kernel, in other words. And of course, you can take the variation with respect to the mass, you can take the variation with respect to the angular momentum, or you can take the variation with respect to any diffeomorphism in the general covariance, in which case, in fact, you will end up also with the Lie derivative of the Kerr metric with respect to any vector field in the kernel. Okay, so the first kernel here, the first part of the kernel is finite dimensional. It has in fact dimension 4 because you should count the angular momentum as a vector. Both the norm of the vector is what I call A, and then there is the direction of the axis. But this kernel here has infinite dimension. It has the dimension of all vector fields. Okay, so it's a much more serious kernel. So of course, if you have a kernel, and if you go back to my analogy with linear systems, obviously you cannot solve the system except if you make sure that you solve orthogonally to the kernel and that the right hand side is in the co-kernel. So that certainly means you cannot solve this linearized problem in general, but at the same time, at the nonlinear level, there was still this conjecture, which means that at the nonlinear level, in fact, what you need to do, what this kernel reflects, is the fact that you will have to change, you will have to track the change in mass and angular momentum and in diffeomorphism. In other words, you want to, during your evolution, you want to be able to track how these parameters change, and you want, in fact, to track the final parameters. Otherwise, you will not. Otherwise, even though the solution converges, you yourself will not be able to tell. Okay, so this is in fact a standard. This is called modulation theory. When you track parameters during when you look at stability of a multi-parameter family, but it's usually done in finite dimension. And here, really, an interesting part of the problem is that there is this infinite dimensional part of the kernel, and this is really. So this issue of modulation in infinite dimension is really what I want to focus on in the second part of the talk, in the last part of the talk. Okay, so once you have understood that there are obstructions, let me now come back to decay for the linear probability system. So we saw in Sergio's talk, so there was for the Schwarzschild case, this was done by Defamot-Sotzker-Roliansky, and then later on in different gauges by Henkel and Wong, Johnson and Hung. And then for the, yeah, sorry.
Already for this infinite dimensional kernel, so that really corresponds to your choice of gauge.
Yeah, correct.
Correct. This is
so what happens if you want is that you are at initial data, you are given a certain gauge in which you are told that you are in that gauge close to Kerr. But of course, the point is that the black hole during evolution will change. So parameters will change, but also the gauge, in other words, the gauge in which you recognize. If you want, you could still keep the same gauge, but then you will not recognize Kerr, because the way I recognize Kerr, let's say, for instance, is I recognize it in Boyle-Nyquist coordinates. If I gave you Kerr in an arbitrary coordinate system, you will not be able to tell that it's Kerr. So
dimensional part of your modulation theory is keeping track of the gauge choice you have to make to
exactly. Adjusting the gauge is key. You want to keep adjusting the gauge to put yourself in the gauge in which you recognize Kerr. So I want to put myself in a gauge in which I recognize my solution as being the Kerr part plus a perturbation, but the Kerr part is the one is my favorite representation of Kerr. I choose the favorite representation of Kerr, and I want to see my solution as my favorite representation plus perturbation. If I do not adjust the diffeomorphism, there will be another form of Kerr which I will not recognize, so I will not be able to tell that this is Kerr perturbation. So even though solution converge, you're right, it's an issue of gauge. So you could tell me the solution converges. It does converge, but I will not be able to tell. Thanks for the question. Okay, so now, yeah, sorry. So this finishes what I wanted to say on linearized model. And now let me come back to nonlinear models, because you don't want to attack the conjecture directly. You want first to look at nonlinear models. And here, I apologize, there are also simpler nonlinear problems. I will only talk about nonlinear problems that actually solve the Einstein equations. Okay, and here the first such result is the seminar work of Peter and Andras, where they, in fact, so of course, if I say models, I want to simplify something. So there are at least two ways that I know that were tried. One way is, in fact, to modify slightly the equation to add a positive Cosmos-Gel constant. Okay, so what this changes is that it changes the decay of linear waves. So if you look at the linear operator, the decay you expect now is exponential as compared to the asymptotically flat case, where you only get a small polynomial decay. Okay, and this here I should mention I wanted to say something important, so I apologize. I should have mentioned that the framework I'm explaining, in fact, Peter and Andras brought very new techniques to the field, and in particular, which are of spectral nature. So the result I mentioned before for this result here by Peter and Andras, and the result of Pascal Millet actually follow from these techniques, which are fairly different and much more spectral nature than the other results that I mentioned. Okay, so this allowed them. So the analog problem of the Kerr stability is the Kerr de Sitter stability of Kerr de Sitter, and they obtained the nonlinear stability of Kerr de Sitter in 2016 using their new spectral method. And this was, let me also mention that this was later reproved by Ian Fong. Okay, another simplification you can do is, if you want to look at the Kerr stability problem, is to stay in the asymptotically flat regime, in which case you still have to deal with this slow polynomial decay of your linear perturbations, but you want to make your algebraic structure simpler. And in particular, you want to look at the particular case A is equal to 0, which is Schwarzschild, because, of course, Schwarzschild, well, actually, I did not write the formula, but we saw it a lot in the conference. So I think everybody knows the Schwarzschild solution is algebraically much simpler than the general Kerr solution. And in particular, it doesn't have one of these annoying issues that I mentioned of non-integrability. The null frame here, the principal null frame is integrable. Okay, but of course, this is, there is something annoying with this, which is that if you start close to Schwarzschild, the conjecture tells you that you end up close to Kerr. But there's nothing you can do about it. You end up close to Kerr. So if you really want to force stability towards Schwarzschild, the only way you can do it is by restricting the class of perturbations. In other words, you cannot. This is not anymore a stability problem. So you restrict the class of perturbations to make sure that this class the final evolution necessarily is Schwarzschild. In other words, you force the final evolution to have angular momentum 0 to be able to talk about stability of Schwarzschild. Okay, so the work. So this was also presented by Sergio. So the road we chose with Sergio is to, in fact, look at a symmetry class which is preserved by the flow and excludes Kerr. And this allowed us to prove so this symmetry called polarized. We cannot get into what it is. It's not too important, but this allowed us to prove nonlinear stability of Schwarzschild. And for us, this result was important. First of all, because it somehow gave us a blueprint to approach the true conjecture, which is the stability of Kerr. And also it allows, that's where we developed, as Sergio mentioned, we developed the ideas I want to present at the end of the talk on this modulation in infinite dimensions. And later on, this result was extended to a codimension 3 set of initial data by Dafferno, Solzegel, Ronzionski, and Taylor. Yeah.
And in a few more words, what polarized symmetry means, or perturbation?
No, that's okay. So first of all, there's the word axial. So you are in axial symmetry, but that's not it. It's axial symmetry. Well, actually, you can start in axial symmetry with the angular momentum 0 if you want, and use the angular momentum. But here you use something more. You really use the fact that your Killing vector is hypersurface orthogonal. And if the Killing vector is hypersurface orthogonal, in other words, d by d phi is hypersurface orthogonal, then it's only Schwarzschild that has the property. Kerr always has a non-diagonal term, even d and d phi. Okay, so you have this property, and then first it's preserved by the flow, and it's only Schwarzschild that has it. Okay.
But it means this earlier result is a stability result for Schwarzschild.
Yeah, so in other words, if you start on this symmetry class,
I'm sorry, this is what it says. Now I understand.
Sorry.
Yeah.
So the answer is yes. Once you are this symmetry class, it becomes a stability result because you restricted the set of perturbations. Okay, so finally, let me come back to this result. So again, this was presented by Sergio. I just want to so this is a stability resolution of the conjecture, if you want, for slowly rotating Kerr black holes. And okay, so there's a sequence of 5 papers, but Sergio already went. I mean, describe them. So let me just say that in terms of separation of the proof, the decay estimates, except for the Tucholsky scalars, are in this in the joint work with Sergio from 2021. The modulation procedure is a sequence of 3 works. 2 are joint works with Sergio, and the last one is by my student Wei Shen. And finally, what is left is in particular the non-integral structure, which I mentioned a lot, but unfortunately I won't have the time to go into it. So this is different from the framework of Sergio and Demetrios from the stability of Minkowski. So we have to derive in this paper, which is joint work with Lena Georgi and Sergio. We have to derive a formalism for non-integral structure, and also this is the paper that contains all the hard estimates, the wave estimates. In particular, this is where you get the decay for alpha and alpha bar, and this is where you close derivatives at top order. Okay, so the only thing I want to focus from now on is the modulation procedure, in the hope that the kind of constructions we do could be maybe of interest to this audience. So I want to really just focus on the modulation procedure, and in particular the one in infinite dimension. Yeah, I don't know how much time you have. 20 minutes. Oh, okay, please. Okay, okay, sorry. Okay, sorry. So I should speed up a bit. Okay, let me just mention that we are in the okay, we are doing a so let me just say a little bit slightly about the proof. We are doing a continuity argument. So we initialize, and in this continuity argument, so you should think you're not working with the final convergence. You're working with a finite space-time, and your idea is that this finite space-time has certain bounds, and you want to show that there is no limit to how big your space-time can be, so that in the end, you get both global existence and all the bounds that give you Kerr stability. Okay, and here, if you want to do this, so this is how this finite spacetime looks like, or bootstrap spacetime. It starts, and here it's important to understand that it starts on this special hypersurface, which is in our choice space-like, although that's not too important. But here we choose a last slice in the terminology of Demetrios and Sergio. We choose a last slice here. And this last slice, in fact, you should think as the first slice. In other words, everything is determined in my spacetime by this last slice, because it comes with a foliation by 2 spheres. And these 2 spheres determine the null cones that you shoot from it. And then this null cones gives you a foliation at a fixed R hypersurface here. And this foliation allows you to initialize an ingoing foliation here in the ingoing region. Okay, so in other words, once this is prescribed, everything is fixed in my spacetime. So if I want to make sure that I capture this final diffeomorphism that we discussed, it is there that you have to do it, and this is where you do the modulation. So here, let me single out the last sphere of sigma star, S star, which is the sphere the most towards the future. So this is really the one that has to capture the most the change of frame between the initial frame and the final frame, and then this hypersurface sigma star. So this is what modulation is about. So now the only thing I will describe is how to do modulation for sigma star and S star. And let me mention in particular, it's not obvious on my picture, which is, I mean, it's a Penrose diagram, and as usual, it's compactified, so it's not easy to see. Let me mention that even S star has a very R value. I mean, you should understand that this is constructed for very large R value. Your coordinates are, the analog of my coordinates are in Borel increase is very large on this hypersurface. So this would grow. Sorry. I don't know where. Sorry. Okay, so from now on, I'll just focus on this issue of modulation, which I repeat, it corresponds to the careful choice of the last sphere S star, the constants M and A, and the last sphere sigma star. So in other words, and again, I claim that this is completely analogous to track the final diffeomorphism, final mass, and final angular momentum. And here the main building block is, in fact, so it's in the 2 joint works with Sergio. The main building block is to design a procedure to construct a unique 2-parameter family of preferred codimension 2 surfaces in general perturbations of Kerr. Okay, so first let me First, I want to relate in particular to the seminal work of Huisken and Yao. So, and there are also later works, in particular by Michael. Constructing, in fact, a foliation of preferred codimension one sphere in a 3-Uranian manifold. Okay, so here for us, and I'm going to explain immediately why it's very important. So if you want, you could see it in this framework, but for us, it's very important to actually construct codimension 2 surfaces in a 4-dimensional Lorentzian spacetime. You could not first choose a hypersurface and foliate. It's the opposite. The spheres must come before the hypersurface. So this hypersurface sigma star will be a concatenation of these spheres, so they should come first, and then you get your hypersurface as a concatenation of this particular, as a particular concatenation. Yeah, there will be. I will write it. If I have the time, I'll try to write. Okay. So here, yeah, let me just mention why you want to go. What is this 2-parameter family of spheres? We already have seen it in Kerr. So in other words, I am in perturbation of Kerr, and I want to recognize that I am close to Kerr. And the way I recognize that I'm close to Kerr, there are 2 ways. I want my null frame to be close to the principal null frame, and I want the spheres in Boyer-Linkwitz, which were the spheres of constant T and constant R. So these are not round spheres, but these are, let's say, close to surfaces with the topology of the sphere. So in Kerr, in Boyer-Linkwitz coordinates, I can look at the spheres of constant, fixed T and fixed R, the level sets of T and R. This gives you, well, let me just call them 2 spheres. So these 2 spheres special to Kerr, I want to find them in my perturbation of Kerr. I want to find the analog. I want to find this a way to characterize a preferred family of 2 spheres in perturbations of Kerr. And in particular, you can see that it's of course, a 2-parameter family of spheres because it's parameterized by the lessors of T and R. Okay, so this is why in this statement, it's important to find a 2-parameter family of spheres, of preferred spheres. But of course, it's very important that they are unique, that you really find the correct one. Sorry, apologize. Okay, so here let me just tell you what is the definition. The definition is quite simple. You want to fix well-chosen geometric quantities. So here this will be the trace of chi bar, in other words, the mean circumferential forms, and a third one, which is the mass aspect function. Let me, well, anyway, if you know it, you know. If you don't know, you don't know. It's not too important, but it's a natural geometric quantity associated to my sphere. I want these quantities to agree with their Kerr values. Okay, so this definition, okay, it takes 1 line, so it's very easy to define. What is not so easy is to show indeed that once you have set this definition, you want to show existence of these spheres, and more importantly, you want to show that you can find a unique 2-parameter family of preferred 2 spheres. So there's the uniqueness statement, and furthermore, you want to control them. You want to be able to control the geometry, otherwise the result is not too interesting. Okay, so let me mention why you fix 3 quantities, which might look at first a bit surprising. For a codimension 2 sphere, you should expect 2 conditions. But there is a third condition which has to do with the specific setting which uses null frames. There is always a freedom. When you have a null frame, you can always cook a new null frame simply by rescaling it by parameter lambda, and this will still be a null pair. Okay, so I need to fix this freedom, and this is the role of my third quantity. Okay. Okay, so let me maybe try to explain a little bit how you construct these spheres. And again, I will come to my frames, which was the main object here. So imagine that you have an old frame, E4, E1, E2, E3, and this old frame without primes is a frame which is attached to spheres which are not quite the way I want them. And what I want is to find a new frame and a new sphere, which is the ones I look. So I want these old spheres, the spheres attached to this frame, in other words, the ones that are tangent to E1, E2. These old spheres, S without prime, let's say, they are not quite GCM. They don't satisfy these magical quantities that I want. So I want to perturb the frame and the sphere such that a sphere adapted to this new prime frame now has the good properties. So the way you do it is that you change. So here the parameters you have. So let me just mention that how to go from one frame to the other. This involves the scalar parameter lambda, and the one forms NFF bar. And of course, because you are in perturbations, the 2 frames are close, and close is the fact that lambda is close to 1 and FNF bar and small. Yeah.
These spheres, the value of the expansions that you are prescribing, are they constant?
So, well, they are, well, okay, so what I didn't say is for larger. So you don't need to take them constant. In that case, because we are larger, in fact, it suffices to take the Schwarzschild values, which themselves are conformed on each sphere, right? That helps. But okay, for now, let's say that you would even achieve the Kerr value. For us, it's even simpler to just take the Schwarzschild. You could achieve the Kerr value, but in a perturbative regime. So the perturbative regime consider is larger. Anyway, that's where we need them. In this, if R is sufficiently large, then you could do the Kerr values, but it's sufficient to do the Schwarzschild values, and they are constant. Okay, so then you look at the change. What you want to do is how the curvature and the connection coefficients change under this change. So you see that here I'm writing the value in the new frame is the value in the old frame plus linear terms plus quadratic terms, and I will forget the quadratic terms later. And for the gammas, it turns out, and for the connection coefficients, you also have first derivative of your frame or change of frame coefficients here that pop up. Okay, let me maybe just tell you what happens if you adapt this change of frame to alpha and alpha prime, alpha bar and alpha bar, alpha and alpha bar. If you do it for alpha and alpha bar, then there are no linear terms that pop out, and this is why these coefficients are so important. This is why you call them gauge invariant, is that at the nonlinear level, if you did an error in your frame, it wouldn't matter too much because it would lead to quadratic perturbations. Okay, so this is why these components are always important, and you always retrieve them first. Okay, but now let me apply this change of frame to my three favorite quantities, trace chi, bar, and mu, so the expansions and the mass aspect function. And if you do this, you see that what pops out are something which starts looking like an elliptic system for the change of frame coefficients. So this is always so this denotes the divergence of a one form, and this denotes the Laplacian of my scalar on the new sphere. The prime is on the new sphere. Okay, so you get an elliptic system on the new sphere once you want to prescribe the values to be exactly what you want. Except that, of course, it's a one form, so the divergence is not enough. You want a curl if you want an elliptic system. So where does the curl come from? The curl comes from the fact that so far it's a general null frame. It's not necessarily adapted to a sphere. So if you want to make it adapted to the sphere, you have to require, it's necessary and sufficient to require that the anti-symmetric part of the second fundamental forms are zero. So this is these conditions here. These extra conditions is what we call the anti-trace. You want to take you want to force the second fundamental form to be zero. And this, once you do the change of frame, this is what gives you the curl of S7 bar. And now I have an elliptic system. Okay, so if I want to solve a priori, at least I get an elliptic system for F and F bar in terms of a Diffie system and a Laplace equation for lambda. Okay, so then, so this is just a review of my previous slide. If I want to fix these quantities at the level of change of frames, this means deriving an elliptic system for the change of frame coefficients. Of course, an elliptic system, I just showed you the higher order term, but the lower order term matter if you want to solve it. And in particular, you could have a kernel and a co-kernel, which would prevent you from solving it. Okay? And in fact, it's not quite what happens. There is not per se a kernel, but you have to remember I'm doing things at large R. And at large R, I have to care, if I don't want to lose control, I have to be able to uniformly invert my system, even if R is arbitrarily large. And if I do this, I will have to start caring about Minkowski, because I'm in an asymptotic flat case. My spheres, of course, the spheres I wrote, this S of TR, they converge to the round spheres of Minkowski. So I have to understand how many of my magical spheres I have in Minkowski. And unfortunately, in Minkowski, there are more spheres, simply because in Minkowski, so in Minkowski, well, let me write so what I call GCM as general modulated GCM, general covariance modulated sphere, because it's the modulation due to general covariance. So if you look at the GCM spheres in Minkowski, of course, this I can write because it's very easy. Well, the other ones are not very difficult either, actually. Then the values you get in Minkowski, simply you look at trace chi is 2 over R, trace chi var is minus 2 over R, and the mass aspect function is 0, which means exactly the round spheres of Minkowski. Okay. So the question is, how many of such magical spheres you have? Well, you have your two-parameter family of spheres. In other words, the spheres at t located at the origin at t is equal to constant, okay, and with radius r. So now these are the round spheres. But of course, my conditions are invariant as soon as I choose an isometry of Minkowski. So I just have to look at the isometries which do not preserve my two-parameter family of spheres. And these are the 3 space translations and the 3 boosts. Okay, and for that reason, I generate, in fact, a kernel which has dimension 6 due to the 6 space translation and 3 books. So this is not quite a kernel, but it's an asymptotic kernel. In other words, for large R, I cannot invert correctly my system if I don't take this into account. So it turns out that because they are generated by translation and boost, the kernel for Minkowski would correspond to, it will live at the L equal 1 modes of the divergence of F and F bar. Okay, and that's the correct counting because, here I mean the analog of spherical harmonics at L equal 1. So you have three for the translations and 3 for the boosts. Okay, so then this means that the first result we obtain is we relax the problem and we first start to construct this 8-parameter family of spheres. So now I have 3 parameters lambda and lambda bar in R3, which corresponds to the L equal 1 modes, the freedom of the L equal 1 modes. And I relax the quantities to be just fixing the trace, but for trace chi bar and for mu, you just fix everything except the L equal 1 modes to be equal to the Kerr value. And then, because you have an added freedom of this lambda and lambda bar, you just use it to fix divergence of F and divergence F bar to be the value of the L equal 1 modes, because this is the part that you cannot quite invert in your elliptic system. Okay. And once you do this, you can, so first 2 things. First, at this stage, you don't have what you want. It's an 8-parameter. I have too many spheres. And second problem, these spheres are not intrinsic. It depends of the old spheres. I want something that is intrinsic, does not depend on the old sphere, so that's very important. But I claim that this is the main building block out of which you get everything. Okay, so then using this freedom, I can in particular get my favorite foliation by 2 spheres, for which I will use the freedom of lambda and lambda bar to fix the L equal mode of trace chi bar. So that gives you trace chi and trace chi bar equal to the Kerr value. Mu is equal to it outside the L equal 1 modes, but nevertheless, you use the freedom to get other L equal 1 modes to be 0, and that's the divergence of this beta. That we saw this curvature component beta that I wrote. Okay, it was at the beginning, so hopefully you didn't forget. Okay, and then this I claim that this is the criteria which gives you this gives you a unique 2-parameter family of spheres, and inside this unique 2-parameter family of spheres, I choose my last sphere S star of the spacetime, the ones most towards the future. Okay, so this is how you get it. And then modulation, once you have S star, you still need to find A and M and the final sphere and the final hypersurface sigma star. So let me now move to the rest of the modulation parameters. M is simply chosen to be the Hawking mass of S star. So this is what you expect. It's very easy. But now for A, there are lots of, if you give me a sphere S star, there are lots of definitions of angular momentum on a sphere in the literature, but it turns out that none of them was working for us. So we come with yet another definition, probably not so natural from a physical point of view, because it lives at 1 derivative of the curvature. So you take, since you fix the divergence of beta, you have the freedom of the curl of beta, and you use the curl of beta to define your angular momentum and the axis, because you need to, you don't have any symmetry, but of course you're converging to Kerr, which has an axial symmetry. So you need to track what is the final axis of symmetry. So this, you do everything with curl beta. Simply you take your basis of L equal 1 mode, you rotate it such that the non-axially symmetric L equal 1 modes the projection on non-axially symmetric L equal 1 modes vanish on curl beta. And finally, you take the axially symmetric L equal 1 mode, in other words, cosine theta on the round sphere, you take this L equal 1 mode to give you a definition of A, which of course is chosen so that in Kerr it agrees with the actual value of Kerr. Okay, so that's how you fix your L equal 1 modes. And here, again, I want to insist on having only intrinsic quantities. And here there is something which is a priori not necessarily intrinsic to the sphere, which is how you define the L equal 1 modes. So you need an intrinsic definition of L equal 1 modes. And for this, what we do is we use the uniformization theorem to pull back the L equal 1 modes by uniformization map, but we need an effective version. In other words, we need really, usually uniformization theorem in the literature is not more about existence, but here we really need the stability of the uniformization map with respect to when you compare different spheres. Okay.
Wouldn't you use the second, third, and fourth eigenfunction?
You could use it, yeah. I think you could use it, yeah. That's another possibility to use the exact eigenfunction of the particle elliptic operator. You're correct. You could do that. Yeah, you could.
But you still need the effective version.
Well, yeah, probably to control. Well, I mean,
stability is done.
No, but what he means is you take the even that you have Laplacian, you can take the actual eigenvalues of your. You could do that, and I think you can. Okay, and finally, okay, and let me, that's my last slide. I hope I'm still controlling the time. Okay, so you want to start now, you have S star, you have the parameters, and you want to construct sigma star. So here we use the procedure by Dawei-Shen, which extends your work in Schwarzschild to the general case of perturbations of Kerr. And here the idea is you should think of this result. You have this family of spheres, and you're going to choose your spheres, a concatenation of some of these spheres, but indeed there is this freedom of parameter lambda and lambda bar, and you use it to get extra conditions. So I guess this was the question of Michael. You use it to get extra conditions. This gives you extra conditions on this hypersurface, in addition to just be a collection of spheres. Of course, it's not just a collection of spheres. Of these GCM spheres, you get, in fact, 6 extra conditions from the L=1 nodes. And then you should see it as a local existence result. So you start from S star, and then you apply this local existence result. And as long as your bounds hold, you can apply it all the way to initial data where you stop. Okay, and here I should mention, and in particular, what is important here is that your gauge is really initialized from the future without any reference to the initial data. This was really, in fact, the first time this appeared was in our work in Schwarzschild. And this is well, first of all, I think this is really impossible to do without, if you really want to track the final state. But this, of course, you have an additional difficulty now that the gauge in which you measure your decay is defined from infinity, or from the future if you want, while the gauge in which you know you are close to Kerr is defined at initial data. And there is a non-obvious way, I mean, there's an obvious question, why should this gauge be related? So then you really have to bring some information back from this sphere S star here, in fact, the L=1 modes, and then you have to have some rigidity properties of the GCM spheres to be able to conclude. Okay, thanks a lot for your attention.